It's a pleasure to introduce to you Ziv Bar-Yossef, who's here from Google, actually. He was with Technion until 2 weeks ago, so he's a Noogler. He's going to tell us about how to randomly sample from a search engine. This paper won the Best Paper Award at the 2006 World Wide Web Conference, so it should be an interesting talk. This is an externally visible talk. It's going to be put on video.google.com, so please make sure that you exercise your judgment when asking questions or making comments. Thank you.
Thank you, Shiva. And this is joint work with my student, Maxim Gurevich. So I'm going to talk about random sampling from a search engine's index. Before I talk about our contributions in this work, let me start with a brief description of what is the problem we were trying to solve. So all of you are familiar with how a search engine is built and looks like, and this is a very high-level picture of a search engine. The main data structure is the index, containing posting lists, where each term is associated with one posting list. And the posting list consists of pointers to documents on the web that contain that term. And we denote throughout this talk the set or the corpus of documents that are pointed by the index by D. We call it the corpus of the search engine or the corpus of index documents, or sometimes we just simply call it the index, although we just mean the corpus of the documents. Now, standard users do not have direct access to the index. They cannot get any data directly from the index. The only possible way for them to get information from the index is via the public interface of the search engine. Okay, so users can submit queries and get back results. What we would like to do is to create a sampler, which is a computer program that interacts with the public interface of the search engine. So it can send queries like users and get back results. After submitting queries and getting back results, somehow magically the sampler should produce a random document, X from D. Note that for internal users, it's very easy to generate these random documents because they have this privileged full access to the index. However, for external users, it could be very hard to sample documents from D.
It's okay if you use the other screen.
Okay. Let me step here.
When you say random, you mean uniformly?
That's a good question. Actually, our sampler can work with arbitrary target distributions over D. But for the purpose of this talk, let's think about the target distribution as being the uniform one. That turns out to be the most difficult case. Okay? It would be, can we? Okay. Now, one technical restriction that all search engines have, that when a user submits a query to the search engine, if there are many, many matches, the search engine does not return all matches. It just returns the top K matches, where K is a cutoff parameter, depending on the search engine. In Google and Yahoo, it's K equals 1,000. In MSN, it's 250. And this is a severe limitation that our sampler will have to deal with. Why do we need search engine samplers at all? Well, it turns out that if you have a search engine sampler, this could be very handy in creating objective benchmarks for search engines, and we can use them to evaluate the quality of search engines. For example, you could test the freshness of the search engine. What fraction of the documents in D, in the corpus of the search engines, are actually alive? You can test topical bias. For example, you can compare which of the search engines covers better the .il or .edu domain. You can Why is it happening?
I don't know. Somebody's doing something remotely. I don't have any control over what's going on.
It's going to be very confusing if this talk continues like that.
Ask the people in the remote offices to stop pushing buttons. They can hear you.
Yeah.
You can have
So, people at the remote offices, please stop pushing buttons because we are getting confused here. You can test spam. You can check if you have a good spam classifier. You can try to see what fraction of the pages in the corpus are spam. You can check the security resilience of the search engine, whether what fraction of the pages are contaminated by viruses or worms. And probably the most interesting part for you guys, you can check relative sizes of search engine. You can check which search engine is larger, Yahoo or Google. So it turns out that size wars between search engines are almost as old as search engines themselves. And the latest rounds in the search engine size wars erupted last August after Yahoo announced that they indexed over 20 billion documents. At the same time, Google reported on its homepage that it indexes only 8 billion documents, but shortly after, it came out with its own announcement that its index is 3 times larger than the competition's. So this clearly doesn't add up, and it calls for objective methods to measure search engine size. We can see from this that we cannot just rely on search engine reports. They are sometimes misleading. Why do we care about size? Search engine size, first of all, is just a measure of how comprehensive the crawler of the search engine is. A good crawler is one which is able to fetch and cover the most documents possible. And search engine size could indicate whether the crawling is doing a good job. It also indicates the ability to answer narrow topic queries, queries for which there are very few results, like navigational queries. Either the search engine has the right result or it doesn't. A large search engine has the ability to answer a wide variety of such narrow topic navigational queries. Probably the real reason why people care about search engines is just a matter of prestige. Search engines like to boast these size numbers because they think people may be impressed. The question of measuring size of search engines from the outside was studied quite a bit from 1998. One method to do that is similar to what we are doing here, is to sample pages uniformly at random from the search engine's index. How do you use such samples to estimate size? And there are two possible ways to do that. If you really want to know the exact absolute size of the corpus, the only way I know to do that is the following. You just generate samples, independent samples, one by one, until you hit a collision. A collision meaning that you got the same document twice. By a simple probabilistic argument called the birthday paradox, it's easy to show that you expect this first collision to happen after about root n steps, where n is the real size of the search engine. So if you got the collision after k steps, you can estimate the size of the search engine as k squared. The problem with this approach, that as n is very large, also k, the number of samples you need, is very large, and it may be prohibitive to send so many queries to the search engine just to estimate its size. So the approach that was taken so far is to estimate relative size rather than absolute size. Suppose now you want to find what is the relative size of Google versus Yahoo. What is the ratio between the size of Google versus the size of Yahoo? You will not know the absolute sizes, but at least you'll know which is bigger and by how much. To do this estimation, you don't need that many samples. You need very few samples from Google and test then whether how many of them are also in the Yahoo index and vice versa. Okay? And from these two numbers, you can estimate the ratio. That's the approach we use in our paper. There are other approaches for measuring size. Some are just based on anecdotal queries. Just you can see articles, mainly news articles, where they say, we checked these 20 queries and it looked like that the Google results were much better than the Yahoo results. And from this, they somehow conclude that Google is bigger or better than Yahoo. Of course, these kind of studies do not have any theoretical or statistical guarantees. A somewhat more principled approach is not just to use anecdotal queries, but rather queries taken from query logs. You track all the queries submitted by users over a span of 3 days in some organization, and then you submit these queries to each one of the search engines and somehow process the results and conclude about relative sizes. Again, there is no guarantee about what the distribution of queries in these user query logs, and therefore it's hard to conclude anything about the relative sizes from these experiments. A different approach is to use random samples not from a search engine, but rather from the whole web. If you could somehow sample pages from the whole web and then test what fraction of them belongs to Google, Yahoo, and so forth, you can get accurate estimates of their sizes. And there were several studies that addressed this problem. However, this problem is much harder than just sampling from a search engine, and therefore the methods known suffer from certain biases, which means that also the estimates they produce are not very accurate. The main previous work before ours was due to Krishna Bharat and Bharat-Broder, a Googler and a Yahoo person nowadays. And while they were both at DEC, I think, they invented the following method to generate random samples from the search engine. So in their method, there is a pre-processing step where they crawl a large corpus. They crawl the Yahoo directory at the time. And from the large corpus, they create a lexicon of terms. This is simply all the terms that occurred in documents in that corpus. They attach to each term frequency, estimate of the frequency of that term. This is simply the frequency of this term in the document in the corpus. And the thought here is that since the corpus itself somehow represents the whole web, also these terms and their frequencies represent the frequency of terms over the whole web. Now, what would they do with this lexicon? Yes? How did they choose the terms? I don't remember exactly. They just took, I think they took all the tokens, all possible tokens. Okay, now given a lexicon that was created in this pre-processing step, the sampler works as follows. It somehow chooses two terms, T1 and T2, from the lexicon. These are not chosen independently. They use the frequencies to choose these two terms. And then they submit a conjunctive query to the search engine. Get me all documents that have both T1 and T2. Okay? They get back from the search engine the top K matches. And now they just pick a random match from these top K and return it as the sample. So now the question is, why does this give a random sample from the corpus D? Well, you can prove that under two assumptions. First, if all queries return exactly the same number of results, and moreover, all of them return less or at most K results, and secondly, that all documents are of the same length, then the samples are indeed uniform. Well, you can see right away what the problem is, that these two assumptions do not hold in reality, which means that the samples have bias. They are not really uniform. The major bias is towards long documents. Long documents are much more likely to be sampled using this approach. The reason is that they just match many more pairs of terms. So it's much easier to find terms that will match long documents. The second problem is bias towards pages that have high static rank or high page rank. Even though the choice of the terms they used was meant to return less than k results, sometimes these terms return more than k results. In that case, they just choose among the top k, meaning that matches that are beyond the top k have 0 probability to be selected. So documents that have low static rank have very little probability to be selected, and therefore this method favors highly ranked documents. So what are our contributions? We created 2 new search engine samplers. One is what we call a pool-based sampler. It's based on a pool of queries which is very similar to the lexicon of Bharat and Broder. We could actually prove that under plausible assumptions, this sampler generates near uniform samples. And we can quantify the distance from uniformity. We proposed another sampler, which we call the random walk sampler. This sampler runs a random walk on a virtual graph. The nodes of the graphs are exactly the documents in D, the documents indexed by the search engine. And you can show that if you run the random walk for sufficiently many steps, it will converge to the uniform distribution. So you just run the random walk for many steps and stop, and that's your sample. The main advantage of this sampler, just a second, is that it doesn't need this pre-processing step. It doesn't need an explicit lexicon or query pool. So it's easier to run. However, turns out that it's less efficient. It requires more queries to the search engine in order to generate each sample. Yes?
You keep talking about a uniform distribution. Along what measure? I mean, uniform in what sense?
You were asking, I have to repeat all your questions for this video. So the question was under what measure is this uniform distribution is. I just mean that each document in D is equally likely to be selected. Each has 1 over the size of D probability to be selected by the sampler. And the probability is over the choices made internally in the sampler. The sampler will toss coins, choose random queries in some way. So it's over that measure, if I understand your question correctly. Okay. Due to lack of time, I'll focus in this talk only on the pool-based sampler. Be happy to talk to any of you later offline about the other sampler too. So let me start with the simple abstraction of what a search engine is. And we view it as a bipartite graph. So let's look at this small search engine. It has only 10 documents in its index. And now let's fix a pool of queries. This is just a selection of queries that you can submit to the search engine. In this case, we selected 4 possible queries: news, BBC, Google, and maps. So the nodes of the graph, on one side it's the documents, on the other side it's the queries in our pool. Now edges are defined by how the search engine replies to queries. For example, when we submit the query news to this search engine, it returns the first 4 documents, and therefore we connect the node corresponding to news with the 4 nodes corresponding to these news sites. Okay? Similarly, when you submit the query BBC to that search engine, you return these 3 documents, and therefore we connect them by an edge, and so forth. So we call this the queries documents graph. For a query Q, we denote by results of Q the set of documents returned by the search engine when you send Q as a query. Results of news are the first 4 documents, as an example. Cardinality of Q is just the number of results returned. queries of X, for a document X, queries of X is all the queries in our pool which will return X as one of the results. For example, queries of www.cnn.com is just news, because the single query here that returns cnn.com as a result is news. However, queries of news.bbc.co.uk has two items, both news and BBC. We call the degree of the document just the number of queries that return that document as the result. So the degree of CNN.com is 1, but the degree of BBC COUK is 2. Okay. Now we note the following observation. It's relatively easy to compute cardinalities and degrees, cardinalities of queries and degrees of documents. So how would you compute the cardinality of a given query Q? You just simply submit Q to the search engine. You get back the results. You do not rely on the reported number of results, because this is notoriously bad. You just count the number of results, and that's the cardinality. How do you compute the degree of a document? This is somewhat more tricky. If you assume the pool consists, say, just of terms or phrase queries, then you could do that. Suppose our pool is just terms, like the example we had. So we just enumerate over all terms in the document. We fetch the document, enumerate all terms in the document, and see which ones of them belong to our pool. And that would be exactly the degree of the document. And I'm making here certain technical assumptions about how the search engine works, and that I know that just given the document whether it will be returned by the search engine or not. But I push these technical details right now to the side. And if any of you wants to talk about them, I'll be happy to. Okay, so from now on, we assume that given a query, we can compute its cardinality, and given a document, we can compute its degree rather easily. How do we use these facts to sample pages uniformly from D? So it looks like that sampling pages from D, at least directly, is hard. It's a hard problem. We don't know how to do it directly. However, it will be easier for us to sample documents from D according to a different distribution, not necessarily the uniform one. Okay? Actually, we will show that we can sample documents proportionally to their degree. So this is a non-uniform distribution. It's biased. Documents that have high degree will have high probability to be selected. Documents with low degree will have low probability. The probability to be selected is exactly the degree of the document over the sum of the degrees of all documents in the corpus. So I'll show you in a few slides how we can sample documents from D according to this distribution rather than the uniform one. Okay, this is an example of the degree distribution. Under this distribution, CNN will have 1/13 probability to be selected, while News BBC COUK will have 2/13. Now, we need samples from the uniform distribution, but we will have samples from a different distribution, the degree distribution. So it's a natural question to ask whether we can somehow use these bias samples, the samples from the degree distribution, to simulate sampling from the uniform distribution. Well, since I'm here, you know that the answer is yes. And actually, there is it's a well-studied area in statistics called Monte Carlo Simulation, which addresses exactly this question: how to take samples from one distribution and simulate sampling from another distribution. In our work, we use 4 such methods. And in this talk, I will focus on the simplest one, which is called rejection sampling. Yes?
So, how do you find the degree of a document if you don't have the pool?
How do I find it? I have the pool. Remember, we are in the pool-based sampler, meaning I have the pool explicitly. And I'll talk in the end, how do we create the pool? It's very similar to how Bharat and Broder created their lexicon. Okay, so we have it available. Okay, so what is a Monte Carlo simulator? This is an abstract description of a Monte Carlo simulator. It has some target distribution pi. This is a distribution we want to sample from, but it's hard to do it directly. In our case, pi is the uniform distribution over D. On the other hand, we have P, which is the trial distribution. This is a distribution on the same space, which is easy to sample from. In our case, P will be the degree distribution over documents. A Monte Carlo simulator needs to be able to compute what we call bias weights. For each instance X, in our case, for each document X, we need to be able to compute the bias in P relative to pi. Meaning we need basically to compute the ratio between the probability of X under pi and its probability under P. And these hats are intentional. You'll understand in a second what they mean. And I'll show you that we can, in our case, we can compute these bias weights. In fact, in our case, the bias weight of a document X will be just 1 over the degree of that document. And I already mentioned to you that we know how to compute degrees. Therefore, we can also compute bias weights. Now, using these bias weights, a Monte Carlo simulator works as follows. Remember, it wants to generate samples from pi, but it has samples from P. So it will use a P sampler, a sampler that generates samples from P. It will repeatedly invoke that sampler to generate samples, X1, X2, and so forth. For each one, it will compute these bias weights, W of X1, W of X2, and so forth, and then feed the samples and the bias weights into the Monte Carlo simulator. The Monte Carlo simulator is just an algorithm. It's a simple, and we'll see one example of such an algorithm in a second, which somehow processes the samples and the bias weights and then generates a single sample from pi. Note that you may need multiple samples from P to generate a single sample from pi. What are these bias weights? In order to define them, I need to define what is an unnormalized form of a distribution. A distribution is just, in our case, we talk about a discrete distribution over finite domains. So these are just functions from the domain to the interval 0, 1, and they sum to 1 over the domain. An unnormalized form of a distribution is the same as a distribution, but it's multiplied by some normalization constant, which could be unknown. Okay, so pi hat of x is just pi of x times the normalization constant z pi. And note that it's the same constant for all x. It's independent of x. To make this definition more concrete, let's consider an example. For example, suppose pi is the uniform distribution, like in our case. So the simplest unnormalized form of pi is the following. For each x, we assign the value 1, constant. It's always 1. And note that indeed pi hat of x equals pi of x. Pi of x is 1 over the size of d, times the normalization constant, size of d. So in this case, the normalization constant is the size of d, and the unnormalized form is the constant function 1. What about the degree distribution? In this case, an unnormalized form of the degree distribution is simply the degree of x. Okay? And the normalization constant in this case is the sum of the degrees over all documents in the corpus. The bias weight, if you remember, is just the ratio between the unnormalized form of x under pi and the unnormalized weight of x under p. So we don't really need to know pi of x and p of x. It's enough to know pi hat of x and p hat of x. And these are easier to compute, at least in our case. For x, pi hat of x is just 1, so we know it right away. For p hat of x is just the degree of x, which also we argued it's easy to compute. So in order to find these bias weights, we don't need the normalization constants that are unknown, the size of d and the sum of the degrees. Okay, I have about 30 minutes, so I think I have time. Let me quickly show you one such Monte Carlo simulator. It's the simplest one known due to John von Neumann. It's called rejection sampling. This simulator needs to know what we call an envelope constant. It has to be given a priori. It's a constant that is guaranteed to bound the bias weight for all x's. So you need some upper bound on the bias weight of all x's. In our case, it's very easy to find this bias weight, this constant, because if you remember, the bias weight in our case is 1 over the degree. This is a value which is always at most 1. So we just use an envelope constant, c equals 1. Now, the rejection sampling algorithm works as follows. It repeatedly generates, in an infinite loop, samples from the trial distribution P. For each sample, it invokes an acceptance-rejection procedure, which decides whether to accept the sample or not. If the sample is accepted, it is output as the sample from pi, and the procedure stops. Otherwise, it's just tossed away, and a new sample is generated. So it continues until one of the samples is accepted. How do you determine whether to accept a sample or not? That's easy. You just toss a coin it's not a fair coin, it's not half-half, but rather it has different probabilities for tails and heads. The probability for heads is the bias weight. Remember, we know how to compute the bias weight over the envelope constant C. Note that the envelope constant guarantees that this is a proper probability. It's a value between 0 and 1. And now if the coin comes up heads, we just accept the sample. As I said, in our case, C equals 1, and the acceptance probability is just 1 over the degree. It may look somewhat abstract, but it's easy to see what happens in our situation. In our situation, P is the degree distribution, which is non-uniform. Pi is the uniform distribution. So what basically the acceptance rejection procedure is doing is smoothens the degree distribution. Samples that have a priori high probability to be selected because they have high degree will be accepted with low probability. On the other hand, samples that have low probability to be selected a priori because they have low degree will have high probability to be accepted. So overall, you get that all documents will have the same probability to be selected. It's a rather simple probabilistic argument. Okay, so how do we use rejection sampling to create our sampler? So, as I told you, we have some way to create samples from the degree distribution, and I'll show you in a second how we do that. This has to interact with the search engine somehow, and then it generates samples from the degree distribution. It feeds them into a rejection sampling procedure. The rejection sampling together with these bias weights, and then the rejection sampling procedure just outputs a uniform sample from D. So it's very, very easy. So the main question to be asked is, how do we sample from the degree distribution? If we do that, we are done. Okay, so let's see how we can sample documents, but now by their degree, not uniformly. So here is a naive way to do that. We just select a random query from our pool. We said this is an explicit pool. We have it, so we can select one of these queries at random. Suppose we selected BBC. And now we choose one of the results. We submit that query to the search engine, get back the results, and choose one of the results at random. Say in this case, we chose news.bbc.co.uk. It's very similar to the Bharat-Broder approach, by the way. And then you just output that as the sample. Well, you could see that indeed documents with high degree have higher probability to be selected, simply because they match many more queries. However, what we get here is not exactly the degree distribution. Let's compare, for example, two documents that have the same degree, CNN.com and the Wikipedia page of BBC. Both have degree 1. But I'm claiming that they do not have the same probability to be selected under this process. Can anybody see why? Yeah? You there?
Things goes to BBC.
Exactly. So you could see that CNN shares its resource, the query, with more results. There are 4 results for news, but only 3 for BBC. Therefore, the probability of CNN to be selected is 1/4 first to select news, and then 1/4 to select CNN among the results of news. So this is a total of 1/16. However, the Wikipedia page has 1/4 probability to select BBC, but then just 1/3 to select the Wikipedia page. So it's 1/12. So it has higher probability to be selected. So we see 2 documents with the same degree, but with different probabilities to be selected, which means that this process does not generate documents according to the degree distribution. How can we fix that? If we could somehow sample queries not uniformly, but rather proportionally to their cardinality, meaning that queries with higher cardinality will have higher probability to be selected, then we will be fine. So we will choose the query news with higher probability than the query BBC, and that will fix the mismatch between CNN.com and the Wikipedia page. Okay? So here is how you would do that. You choose news with probability proportional to its cardinality, and then you select a random document from its result set. And here, this is an analysis I will not go into. That it's just a one-line analysis that shows you that this is good enough. If you can do that, you can sample documents by their degree. Yes?
So do you assume that
No. I'm not assuming that I queried all the queries in the pool. That's something. Usually pools are very, very large. In our experiment, for example, we had 650 million queries in our pool. So you cannot expect to submit all of them to the search engine. And you indeed found the main problem that we'll have to tackle is how do you know cardinalities of queries? Okay, yes?
What about conjunctive queries? I mean, if you have combination of queries, does that have to be complexity if you have like queries such as news and BBC?
Yes.
So is that modeled by your...
I think it's modeled.
Can you repeat the question?
Yes. What about conjunctive queries like news and BBC? Is it modeled by our setting or algorithm? I don't see the real difference here. But there are other reasons not to use conjunctive queries, and that's why we don't use them. Yes, April.
If you're doing a comparison of engine size, like your example, right, are you going to sample the queries and then pick both engines with them?
I didn't hear the last part.
If you're doing a comparison of engine size,
Yeah.
you can use the same queries on both engines.
So the question is, when we use the samples to estimate relative sizes of search engines, do we use the same queries with the 2 search engines? So I think the answer is not. No, we don't use exactly the same queries. Yes?
The role played by the normalization constant
Yes.
free. I mean, you chose 2 constants that were not comparing.
Right.
So you have complete freedom in choosing these normalization constants because the theory covers and it's fine, or you had to, or these specific choices that you made that were somehow constrained.
Okay, so the question is whether we have complete freedom in choosing the normalization constants or this specific choice was important in any way. So I don't think it was important in any way. You just choose constants for which it's easy to compute the unnormalized form. For the uniform distribution, it doesn't matter because you choose a normalization constant that will give you a constant function. It didn't have to be the size of D. It could be other things that depend on the size of D, like twice the size of D or so forth. So I don't think it's very important. There is no one choice which is good. Other questions before I go on? Okay. So now, how do we sample documents by degree? Given what I told you, it's easy. We somehow sample queries now from the pool proportionally to their cardinality. And we'll talk about in a second how we do that. We submit the query to the search engine, get back results, and pick one of the results uniformly at random. And by the analysis shown in the previous slide, this really gives you samples from the degree distribution. So the main question now left is how do we sample queries by their cardinality? As Shiva noted, we don't know the cardinalities of all queries in the pool a priori. In fact, it seems hard to sample queries from the pool proportionally to their cardinalities. On the other hand, it's easy to sample queries uniformly. Does this ring a bell? So it's exactly the same scenario we faced before of Monte Carlo simulation. We have one distribution we want to sample from, but it's hard. We have another distribution on the same space, which is easy to sample from. So we can use Monte Carlo simulation again. Now we use Monte Carlo simulation in the reversed way. We want to have biased samples, biased by their cardinality. We have uniform samples. But you could do that as well with Monte Carlo simulation. You could use it in the reverse direction. Okay? So the target distribution now is the cardinality distribution over queries. The trial distribution is the uniform distribution over queries. This slide, I won't go into the details, shows you what are the corresponding bias weights and envelope constants, but just believe me that it works. Okay, so this is the full picture of how the sampler looks like. First, you sample queries uniformly from the pool. You submit them to the search engine. You then know their cardinalities, which you use in the bias weights. You feed that into rejection sampling, and the output now is our queries according to the cardinality distribution, not the uniform one. You feed these queries into the degree distribution sampler, which can now select random results from their result sets, feed that again into a rejection sampling procedure, which will finally output a uniform sample from the document corpus D. Note that rejection sampling is used twice, once to select queries and second to select documents. Yes?
So flashing by quickly on the previous slide, you're using the search engine's cutoff constant as your envelope constant.
Yeah.
Does this mean that when you're comparing two search engines with different cutoff constants that the bias in the sampling method is not comparable?
Yeah. So there was a question, I just ignored basically the cutoff constant. So the question is, how could it be? I'm just summarizing what you said. And indeed, this is a technical detail that I swept under the rug, but actually it's not a technical detail. It's something very important. And you know that it's a good question because I have a slide about that. It's exactly the next slide. So let's see. So the thing that I ignored is indeed this cutoff constant. I assume that when you submit a query, you get back all matches. And that's something that does not happen. Moreover, as you mentioned, different search engines have different cutoff values. So what do we do with these queries, which we call overflowing queries? Queries that have more than k matches. Okay? If we don't do anything, we'll suffer, like the Bharat-Broder sampler, from bias towards highly ranked documents. Documents that tend to be ranked low, we just have 0 or close to 0 probability to select them. And that's not good. So what are our solutions? First, when you create the query pool, you try somehow to create a pool of queries that do not overflow. For example, if you take phrase queries, it's better than taking conjunctions. Conjunctions will be more likely to return to overflow, or even single terms are very likely to overflow. Also, conjunctions are likely to overflow, but phrase queries, if the phrase is long enough, are less likely to overflow. In our experiment, we took phrases of length 5, which rarely overflow. Okay, but you still have overflowing queries. You cannot eliminate that at all. What happens if you happen to choose an overflowing queries? So we just skip it. We toss it away. We don't use it at all. That creates some problems in our analysis. Okay? The problem is that the bias weights we compute are no longer accurate. Because if you remember, the bias weight in our case was 1 over the degree of a document. The degree assumed that you can just look at a document and know which queries it matches. But you will not know from the document itself which of these queries are overflowing and which are not. Now, we are using only the non-overflowing queries, meaning that the degrees, the actual degrees, are different from what we compute. So now what we have is only approximate bias weights. These are not real bias weights, which can totally spoil what rejection sampling and the other Monte Carlo methods do, in principle. So actually a big chunk of our paper was devoted to this question. What happens when you feed Monte Carlo simulators with bias weights which are not accurate? And we analyzed what happens theoretically. It turns out that if the bias weights we use are close enough to the real ones, to the ones we would have wanted, then also the output distribution of the sampler is not very far from the target distribution. And it depends on what we call the overflow probability of the query pool. This is just the fraction of queries in the pool that have more than k results that are overflowing. Okay, so if your pool was indeed constructed in such a way that it has few overflowing queries, it also means that your samples will be very close to uniform. They will not be exactly uniform, but very close to uniform. Okay, and there are accurate mathematical ways to quantify this distance. Any questions? Okay, how do we create the query pool? I already told you that we use phrase queries. Where do we take the phrases from? Like Bharat and Broder, we just crawl a large corpus. We didn't call the Yahoo directory, but rather the Open Directory project. And from that, we created a pool of phrases of length 5. What do I mean by that? For example, here, this is what you do if you wanted to create phrases of length, a pool of phrases of length 3. If a phrase like to be or not to be occurs in some document in the corpus, so you'll put the following phrases in the pool: to be or not, all the overlapping phrases. So it's quite simple. One important point is, know that since we create the pool from some corpus, and this is a relatively small corpus, it's just a few millions of pages, there is a possibility that there are documents on the web that are not covered by this pool of phrases, meaning that none of the phrases in the pool, or that they do not contain any of the phrases in the pool. If you have a document like that, know that our sampler will have zero probability to get to that document. I'm not sure, according to your eyes, I think you didn't understand what I meant. Let's consider a simple example. Suppose my pool had only 10 phrases. It's a very small pool. And now suppose I have a document, none of its phrases is one of the 10. That would mean that if I use my sampler with this pool of 10 phrases, that I will never get to that document, because there is no query in my pool which will return that document as a result. So there are documents that have zero probability to be selected. Now, even if you create a very large pool of phrases, like what we did, 650 million, there may still be documents that are not covered by the pool. For instance, our pool consisted primarily of English phrases. Documents that are written only in Chinese have zero probability to be selected. So that brings the issue of what we call the recall of the sampler. The sampler doesn't generate samples really uniformly from all of D, but from a subset of D. And we want this subset to be as large as possible. We call it the recall of the sampler. If the recall is 1, then we know the subset covers all of D. If the recall is less than 1, then it covers a fraction of D. We were able to empirically estimate the recall of our sampler using phrases of length 5, and it turned out to be something like 80% of English pages in the web. Okay, I will skip the random walk sampler. There is one slide, and I'll go directly to the results of our experiments. So this is an experiment we ran in order to estimate the bias in our sampler relative to the Bharat and Broder sampler. What we did here is we created our own small search engine. We used the ODP, the Open Directory Project corpus, to create a search engine. And then we ran the 3 samplers against the search engine. Why did we have to do that? Because for that small search engine, we have ground truth. We know everything about it. So we can compare the samples to what is the reality. This experiment shows bias towards long documents. We took all the documents in the index of that small search engine, ordered them by size, by length, and then split them into 10 deciles. Then we ran the 3 samplers against the search engine and found what fraction of the samples fell in each one of the deciles. If the samples are completely uniform, you expect about 10% of the samples to be in each one of the deciles. It should be independent of the size of documents. So what you could see here that indeed Bharat and Broder, the Bharat and Broder sampler has very strong bias towards long documents. In fact, more than 50% of its samples fell in the top decile. On the other hand, our 2 samplers had essentially no bias towards long documents. The random walk sampler, since it's slightly less efficient, or it's not slightly, it's less efficient than the pool-based sampler, had some bias to negative bias towards short documents. Okay. Then we ran just the samplers against the 3 major search engines and tried to find interesting data. And this is an experiment from late April, early May this year. And we compared the relative sizes of Yahoo, Google, and MSN. And according to this experiment, Yahoo is about 30% larger than Google, and Google is about 30% larger than MSN. We used the sample to check the distribution of domain names in the 3 search engines. There is some bias in Yahoo towards commercial.com domains. And you could see also interesting things in this lower tail. This is an estimate of the fraction of dead pages in the index. Again, Google is not doing that great relative to the competitors. This experiment, we tried to compare the cached copy of the document relative to what you actually get when you just fetch the document from the web. What you expect the cached document to be as similar as possible to the current version of the page. So the way we did that, how did we do that? We looked what fraction, we checked for each value p between 0 and 1, for each percent between 0 and 100%, what fraction of the samples had p% change between the cached copy and the current copy. So you can see that about 60% of the samples didn't change at all. So in 60% of the cases, all of search engines were fine. The cached copy was equal to the current copy on the web. As you increase the number of changes, you could see that, again, Google is not doing that great because more... oops, I'm confused a little bit here. Sorry, I'm just confused a little bit by the graph. But the graph also, I think, means that Google was not doing great in terms of freshness.
Question. So
yes.
Why does this percentage of words change matter at all? Either it's fresh, either it's the latest copy or not the latest copy. We get how much is
So we checked only text after removing HTML. We didn't want just technical changes to... Excuse me? Sorry. So the question is, why did we check just changes in text and not just... Okay.
Why does the amount of change matter?
By how much? Okay. Why does the amount of change matters and not only whether it changed or not? So if you find documents that change just by a bit, okay, maybe just one word changed, and Google didn't catch it, that's not too bad. However, if half of the page changed, but Google didn't catch it, that's worse. So that's what we were trying to capture here, but I can't really explain it well right now. Yes?
So I guess, I mean, looking at your graph, right, ideally what you want is that all of, like 100% of your index, 100% matches the live version,
right?
Which means has 0% change. So your curve should be steeper. The steeper your curve initially, the better.
Right.
So MSN is the steepest initially.
Exactly.
Better, and then Yahoo and then us.
Exactly. So now it will be hard for me to repeat all of that, but the ideal thing is that for a search engine is to have 100% of the samples at the 0% point here, meaning that all documents match exactly their current version. And the steeper the curve is means that the search engine is doing better, meaning that I'm sorry, I'm getting confused by this slide, so just excuse me. Let's take that offline, okay? Sorry. Yes.
Just back to the question, why does the change matter? Because some pages change a lot faster than other pages, and supposedly Google has to make up for that. It should sample the pages that really change quickly, more frequently than other pages that are more stable.
Okay. You'll repeat that later. Okay, that's the last experiment, trying to find out what fraction of the documents in the corpus are dynamic, and we did just a simple test checking whether there is either CGI or question mark in the URL. And you can see that Google has a much higher fraction of dynamic pages in its index than the competitors. Okay, to conclude, we presented in our work two new search engine samplers. One is the pool-based sampler, on which I focused in this talk, and the other is a random walk sampler. For both samplers, we were able to prove that they are guaranteed to produce near uniform samples under plausible assumptions. And we also ran experiments that showed that these samples have little or negligible bias. That's it. Thank you. Yes, question.
You referenced your paper where you're trying to sample the unconfident web. Have you compared the results that you get for like relative size when you use this technique to what you get when you use your uniform sample from the web to try and do it?
Yeah, so the question was whether we compare the estimates of relative sizes we got from this technique against relative sizes that you could have gotten from sampling from the whole web. So we just don't have anymore the software that we used to sample from the whole web, and it's quite tricky to create it from scratch, so we just didn't do that experiment. Yes?
In terms of the definition of a page for uniform sampling, is a page basically a URL in terms of the fact that if there are two pages that have the same content on two different URLs, that content is going to be sampled twice as often as any other page? Is that?
Yeah, so the question was, what is the definition of a page? Is it just a URL? So yeah, we just think of pages as URLs. So if you have two different URLs with the same content, they will consider two pages. Yes?
What is the overflow?
What was the overflow probability? I think it was something like 10 to 15%. Yes?
Do you have any guarantees on the quality of your samples, like any confidence or anything like that? Any statistical guarantees on that?
Do we have any statistical guarantees about the confidence of the samples? Yes, that's the main part of that paper, all the statistical guarantees. That's when I said that we were able to prove it's near uniform. That's what I meant. Yes?
It seems like you could use your technique to estimate the dupe rate for an engine, and then you could adjust your size, roughly saying that the number of duplicates for each page is the rounds.
So the question was whether we can use our technique to estimate the dupe rate of a search engine and then adjust the size, the relative sizes numbers accordingly. Possibly, we haven't thought about that. Yes?
How do you compute given the pool of the queries, how do you compute the percentage to figure out that the coverage was about 80%? How do you do that?
So the question is, how did we figure out that the coverage of our pool was about 80%? We did it again using our local small search engine, because there we had complete knowledge.
And can you say something from that on other search engines?
The question is whether we can conclude anything from that about others, or about search engines in general, or about other search engines. If you think that this corpus is representative of the web, maybe. But yeah, it's hard to conclude anything really theoretical or guaranteed about other search engines.
So it could bias your relative size estimates?
The question whether it could bias our relative size estimates? Yes, it could. It could mean that if our recall is very, very low, yes, these relative size estimates just refer to the part we sample from. If that part is very small, then the numbers do not mean much. Yeah, that could be. Maybe we can take the other questions if there are any offline, and thank you again.